The ellipse is defined as the set of all points x, y, whose sum of distances to two foci is constant. Foci is the plural of focus, so an ellipse has two foci. And okay, let's kind of explain this definition with a drawing. That'd be helpful. So think of two foci. So they're 2 points. Let's just put them, um, you know, uh, just horizontally apart from one another like that. So we've got focus 1, focus 2. If we were to look at all of the points whose sum of distances from the two foci is some constant. So, pick a constant. I don't, whatever that is, whatever the constant you choose, so long as it's large enough, you will create an ellipse. So the idea is if you pick any point along this curve, this distance added with this distance will always be the same for every point. So if we then, took another point over here and took that distance and added it with that distance, it would be the same total distance as before. You could even go all the way, straight across to the end and back, and that would all of three of these would add up to the same total distance. You can find some, good YouTubes out there where people create an ellipse. Kind of the classic way is to put two pins, in a piece of cardboard or a piece of wood, and then stretch out a string and kind of hold your pencil or your Sharpie or whatever so that the string is taut, and kind of pull it all the way around, and it'll make a perfect ellipse. It's pretty nice. Or you can make one yourself. You don't have to go on YouTube. You can just do it yourself. Okay. Oh, by the way, V1 and V2, there are two vertices, and they are always, on opposite ends beyond the two foci. So you might think like, well, what about this here? Well, we don't give those names, but along this one, um, we call that vertex 1 and vertex 2. Let's see another drawing with some values sketched in. Okay, and I'll show you the standard forms of the equations. Let me just show you this for now. So imagine the same ellipse. This is the center, which is going to be an important part of the equation. The distance from the center to the foci we call C. All right. The distance from the center to the vertex over here on this side we call A, and the distance from the center straight up to that point above it we call B. Of course, these would all be the same distances on the left side as well. So what does that mean for the standard form of the equation of an ellipse? Well, there's two versions. There's the wide ellipse. I've got a wide ellipse here. But there's also a tall ellipse that would be, the same idea but rotated, like kind of, more thin than wide, or more tall than it is wide. Well, okay, so for the wide ellipse, your center is hk. You can see the values of a and b. X minus h squared over a squared plus y minus k squared over b squared equals 1. Okay. If you have an ellipse that is more tall, we think of A as always being the longer of the two. So here I put A going horizontally and B going vertically. But if it was more tall, we might as well just draw it, something like that. There's the center. Then we're going to think of this as A and this as B. So A is always the larger value. Of course, now in this case, C, would be in, the foci would be in there somewhere. There's C. So A and C always are going in the same direction. B is perpendicular. Okay, so in that case, y minus k squared over a squared, because now A is going vertically, so that's going to go with the y, plus x minus h squared over b squared, because now b is going horizontally, equals 1. Really, in the end, they are the same equation. So, I mean, you're adding, so there's really no reason to, to even reverse the order. You might think of y even as in the second position for the tall one. Just be sure that a, the bigger value always goes with, how, if it's tall, then it's vertical, and a goes with the y. If it's wide, then it's horizontal. A goes with the x. All right. Finally, we need to note this. This is going to come in handy. How does C connect with A and B? Well, this is kind of a strange connection here at first. It still seems kind of peculiar to me and non-intuitive for sure. But there's a Pythagorean theorem going on with A, B, and C. Turns out C equals A squared minus B squared. I think if we were in class, I might explain that, or maybe I would ask people if they were interested in me explaining that, because it's very simple. The way you can show it, based on maybe this first drawing. But you definitely would not expect that. So it turns out A is like the hypotenuse. B and C, if we added the B back on this side, are like the legs. So if you looked at this, turns out that distance A, that same length would connect and make that right triangle right there. But if you're curious to see that, ask me about it in the live session, or maybe just, kind of investigate it yourself. Maybe you can prove it. Okay, I'll give you a hint. It comes back to this definition. The sum of the distances is constant. Okay. One more thing we need to talk about the ellipse before we do an example. It's the eccentricity. All right. Now, I don't know if in pre-calc they talk about eccentricity. They did when I took pre-calc, and so I kind of figured everybody talked about eccentricity in pre-calc, but I've heard more recently, since teaching this course, that students were, I just kind of brought up eccentricity, and everybody in the room went, "What are you talking about?" So what is this? Eccentricity is the measure of how elongated the ellipse is. All right, so if it's wider, taller or wider, if it's more elongated, you're going to have a higher eccentricity. If it's more circular, then you have a lower eccentricity. So here's how it works. We call it by E, not E like the exponential, but E eccentricity. The eccentricity equals just the ratio of C to A. All right, which makes sense, if you think about, bring back the drawing, how long is that distance to the focus compared to how long it is to the vertex? And the further out you push your focus, the more elongated this is going to get. The closer in you bring your focus, the more circular this becomes. All right. Anyway, take the ratio of C over A. Turns out E is always going to fall somewhere between 0 and 1. It could equal 0. The closer it gets to 1, the more elongated your ellipse becomes. Or maybe you would say the more elongated your ellipse, the closer your eccentricity gets to 1. Maybe it's the reverse. So where does the circle come into this? A circle is an ellipse, but it's when the center and the foci all merge. So if you push your two foci together toward the center, at the moment when the two foci merge right at the center, then you've got a circle, right? So that would imply that C equals 0. Right? So if you've pushed your focus right at the center, then you've got C equals 0. Well, if C equals 0, then your ellipse is going, not your ellipse, your eccentricity is going to be 0 right when you're circular. Also, A will equal B. I mean, so that's all gonna, all right. Not a surprise there. So what example do I have for you guys? Just another pre-calc version, a little bit harder than the one we did for the hyperbola, or excuse me, for the parabola. Let's check it out. Find the vertices, foci, and eccentricity of this ellipse 100x squared plus 36y squared equals 225. Okay, now you notice it's not in the standard form, although we can get it there pretty quickly. So what we're going to do is simply divide everything by 225. We know in the standard form that that should be a 1. So if we just divide all three parts by 225, we can manage this. We can work with it. Well, dividing all three by 225, like so. And then if we simplify that, we reduce those two fractions. We'll have 4x squared over 9 plus 4y squared over 25 equals 1. Okay, that's reducing, but notice we still don't have the standard form. The standard form should just have x squared on top and y squared on top. You may have also noticed the center is going to be 0, 0. But we can't have these other numbers, these 4s. They got to go. So what are we going to do? We're going to force them into the denominator, but in this, I don't know how clever it is to you, but when we push it down, it'll become the denominator in the denominator. All right? So when we push this one down in here, it becomes 9 over 4. And when we force that 4, 24 over 4, because, well, you know, if you were to do the reverse, 1 over a over b equals 1 over 1 times b over a. So if you want to get, if you've got b over a and you need to push that b down underneath, then that's how you do it. Okay, so we've got the equation in standard form. We were asked to find the vertices, the foci, and the eccentricity. So let's do those one at a time. Starting with, got to change something here, I realize. First, let's identify the center. Well, the center, and we could have probably identified this from the very beginning. The center is 0, 0. What are the values of a and b? Okay, so remember, a is always the bigger one. So that right there is a squared, which would mean a is 5 over 2. Which the smaller one is b squared. So that's, well, that's b squared right there, which means b is 3 over 2. And then maybe even just a rough sketch, just to get our bearings of what's happening. So I can see my center, 0, 0. So a was underneath the y squared, so I know I need to go vertically, plus and minus 5 over 2. B was underneath the x squared in this case, so I need to go horizontally. And so there, just having a sketch is nice. And I mean, right there, I can even identify the vertices immediately. They're always on the longer, we call it the major axis. So 5 over 2, negative 5 over 2. Okay, so we can just go ahead and state that right there. The vertices are at 0, 5 over 2 and 0, negative 5 over 2. They also asked us to find the foci. Well, that we need the value of c. And so this equation comes into place. C squared equals a squared minus b squared. So we'll plug in our values of a and b. Turns out c is going to work out fairly nice. 25 over 4 minus 9 over 4 gives 16 over 4, which means c squared equals 4. And so c equals 2. If we go back to the drawing, C always goes in the same direction as A, so C up 2 and down 2. And so our foci are at 0, 2 and 0, negative 2. Finally, they ask for the eccentricity. Well, now that we have the value of C, that'll be pretty quick. C over A, 2 over 5 over 2. Simplifying becomes 4 over 5. We could use 4 over 5. It's not uncommon to use a decimal, though. 0.8 as the eccentricity. Fairly elongated ellipse there, getting up there near 1. All right, that was fun. Last but not least, the hyperbola is in the next video.